Hi all, we are in the last chapter, so chapter 10, more on chemical bonding, so molecular geometry. We're not going to get into hybridization of atomic orbitals here, so more Lewis dot structures, but picturing them now in sort of 3D space. And so what we're getting into now in chapter 10 is Vesper theory. So we'll go into this. Now this topic is predicting the arrangement of electron groups around the central atom of a molecule. So the Vesper theory or Vesper model is valence shell electron pair repulsion. We know valence electrons are those in the outermost shell meaning the highest value for n. So n being the principal quantum number. If we have some central atom A, for example, and we have pairs of electrons on either side of A, or we have here A, but then we have bonds to different atoms B on either side of A, what Vesper helps us do is predict how far spread out this area of electron density is and this area. So either being lone pairs or bonds. How far apart are those bonds? And we can look at this because we know within each single bond that contains two electrons that are negatively charged. Areas that are negatively charged are going to repel one another. So negatively charged bonds or lone pairs of electrons will repel one another, meaning they want to be as far apart as they possibly can. So to fully spread out, this bond B will be exactly 180 degrees away from this other bond to this second atom B. So the first atom B and then another atom B here. This formula all falls into AB2. So negatively charged space, those electron areas, those regions of electron density will repel one another. How much they repel one another and by what certain angles and what certain geometries is what we're getting into here in chapter 10 with this idea of Vesper. So electrostatic repulsion, meaning two negatively charged areas will repel one another and try to spread out as far away from one another as they can. Bonds will spread out from one another because within each bond that contains two electrons, and then certainly lone pairs of electrons too, will try to spread out as much as possible around the central atom. So within Vesper, we've already jumped into this first example where we have two atoms bonded to the central atom. This is this example here. This is not really a molecule, it's just a single atom with lone pairs around it. So we can't call this AB2, we just call this atom A. This has 4 valence electrons around it. And so this lone pairs together, those will spread out as much as possible and be 180 degrees away from one another. Why is it 180 degrees? Well, if we picture a central atom A like this, and then in a sphere, where this whole area around a circle would be 360 degrees, so a lone pair here, or a different atom here like B, that lone pair and this lone pair, or this bond to B and this bond to B, will be 180 degrees apart, so half the degrees of a full circle. And so while in this structure we see a bond to B and a bond to B, we will also look at non-bonding pairs of electrons as well. So bonding and non-bonding pairs of electrons all centered around some central atom. What we call this is linear geometry. The arrangement of electron pairs is linear, therefore its molecular geometry is also considered linear. We'll get to some examples where this arrangement of electron pairs is different than the molecular geometry, but we'll get there soon. Here's an example not just with AB2, but with beryllium chloride. So beryllium here in the middle, then 2 chlorine atoms. We change that ending to IDE. with one central atom and two bonds to that central atom and no lone pairs off the central atom. We have this region of electron density going away from the central atom, so that's one on this side, and one other region of electron density here. This means in total here we have two regions of electron density. With two regions of electron density, we have linear molecular geometry, and then those two bonds are exactly, or I should say approximately 180 degrees apart from one another. There can be some fluctuations in the bond direction, but ultimately about 180 degrees separates these two bonds. And the reason I'm specifying here regions of electron density 1 and 1, both regions of electron density for this particular compound are bonds. Other regions of electron density can be lone pairs of electrons. Lone pairs of electrons are considered our non-bonding electrons. So non-bonding lone pairs or bonds. And so altogether with Vesper theory, we're looking at the electrostatic repulsions between both bonding and non-bonding pairs of electrons. So far, we've only seen bonding pairs of electrons around the central atom. Soon we'll see a combination of lone pairs and bonds around the central atom. So lone pairs, non-bonding pairs of electrons do count as regions of electron density, as well as physical bonds from the central atom as well. Let's check out this row now. So for an example like AB subscript 3, this is 3 groups to the central atom. So 3 bonds away from A, here's B, B, and B. We call this sort of molecular geometry and this arrangement of bonding electron pairs as trigonal planar. Planar because we're in the plane of the page. So we're not really in 3D space, we're sort of in the plane of the page where this is all flat. So because this is flat, it's in the plane of the page, we can picture this like a flat triangle. All of these non-central atoms and all of these bonds are repelling one another equally, where this angle here is 120 degrees, so 360 divided by 3. So 120 degrees, 120 degrees, 120 degrees separates these different B atoms, the non-central atoms. And these are all bonded to the central atom A. So 3 groups to the central atom, 3 bonds to be particular, no lone pairs yet, notice that. We will eventually see where we have lone pairs. At this point, we're just looking at 3 bonds to the central atom A. We call this trigonal planar. This structure is flat. This is 360 degrees divided by 3 because we have a flat triangle here. So this is 120 degrees. So this bond to this bond are separated by 120 degrees for trigonal planar molecular geometry. So within this class AB3, one example of this is boron trifluoride. So the prefix here, change the ending to IDE. Boron has the element symbol B, trifluoride F3. So for BF3, we would see boron here in the middle, then fluorines on the sides. Fluorines are coming in with 7 valence electrons. So we know we'll see those lone pairs around the fluorine atoms. So trigonal planar, 120 degrees separates this fluorine atom from this fluorine atom from this fluorine atom as well. Next, again, notice we're not looking at any lone pairs off the central atom, just bonds from a central atom. So now we're looking at 4 groups bonded to the central atom. Remember, this is all happening in 3D space. So we picture A, then bonded to B, 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 and B, so 4 Bs in total. The bond angle that works out here for 4 groups around the central atom is 109.5 degrees. Tetra from the root for 4, so tetrahedral is what we call this sort of arrangement of electron pairs and molecular geometry. Why is this still considered electron pairs? Well, we remember that each bond does contain 1 pair of electrons or 2 electrons. So arrangement of electron pairs, that can be meaning bonds as well. Each bond holds a pair of electrons. And again, tetra for 4, so tetrahedral is what we call this configuration. An example of this class of AB4 would be methane. So the chemical formula for methane is CH4, carbon in the middle, then 4 hydrogens coming off of the central carbon. That bond angle there is 109.5 degrees. We call this tetrahedral geometry. So this is sort of our sphere in 3D space, and then the bond angle again here, 109.5 for 4 bonds coming from the central atom. Notice again, we have not talked about one of these bonds actually being a lone pair of electrons. And so we'll get to that just to give you a preview. If we have a central atom and it has 3 bonds to it, but then it has a lone pair from it as well, this is still considered 1, 2, 3, 4 regions of electron density from that central atom. Again, this is a preview. We have not yet seen this where one of those regions of electron density is a lone pair. We've just been focusing on the bonds to the central atom. So 2 linear, 3 trigonal planar, 4 is tetrahedral. Next, let's go into this class of AB5. So 5 groups bonded to the central atom. Again, picture this sort of in a spherical 3D space to figure out how these bond angles work out. What we're looking at here is one central atom A. To most efficiently distribute 5 groups around that central atom A, we want to spread out those 5 bonds, those 5 atoms, as much as possible. The geometry that happens to work out for 5 groups around the central atom is what we call trigonal bipyramidal. Trigonal because we can see 1, 2, 3 groups up top, 1, 2, 3 groups below. So trigonal bipyramidal, you can picture 1 pyramid here and 1 pyramid here. So bi meaning 2, 1 pyramid up top, 1 pyramid below, so trigonal bipyramidal. To most efficiently spread out these 5 groups, we're going to see first a sort of triangle. So that's 1, 2, 3. Then we have a group directly up top and a group directly below. So just looking at this face here, this is a triangle where all these bond angles are 120 degrees. So here's 1 group, 2 groups, 3 groups, all separated by 120 degrees. Then we have 2 more, right? So we need to add in 4 and then 5 below. So then this bond angle here is a 90-degree angle. You can picture it maybe a little bit better in this drawing. So this bond to this bond is 90 degrees, while the bond angles between all of these, 1, 2, 3, that are sort of in the plane, those are separated by 120 degrees. So for trigonal bipyramidal, 5 groups bonded to the central atom. We have bond angles both of 120 degrees and also 90 degrees. Again, all bonds so far. We're not showing yet that one of these groups is replaced by a lone pair of electrons. We will get there. We'll talk about lone pairs being present here as well. This is 5 bonds to the central atom. We call this trigonal bipyramidal. So before we look at an example of AB5, I want to talk about what these groups are called. So these groups are called something different than these groups. The groups going up and down from a central atom are called the axial positions. If you think about a globe, for example, and it's rotating on its axis, so this is an axial position and this is an axial position. In my drawing here, this is an axial position and this is an axial position. So the one's going up and down from the central atom. Then the groups going around the central atom in this direction are called equatorial. So just like the globe rotates on an axis, we also know this direction is the equator. So these three going this direction are the equatorial positions. They form an equilateral triangle where those bond angles again are 120 degrees, whereas this bond angle here between an atom in the axial position and an atom in the equatorial position, that is 90 degrees separation. So the equatorial electron pairs are all 120 degrees apart, whereas the axial bonding pair with an equatorial bonding pair, those are 90 degrees apart. So here we are still in the trigonal pyramidal example, so looking at AB5, and we just talked about these different names for these positions versus the up and down positions. So equatorial going this direction, axial going up and down. So axial versus equatorial. So for trigonal bipyramidal, we have that class of AB5. An example of this class is phosphorus pentachloride. So a phosphorus atom in the middle, then 5 chlorine atoms coming off of that central atom. This is in the axial position. This chlorine is also in the axial position. This chlorine is in the equatorial, this one equatorial, and this one equatorial position as well. So 90 degrees separation here, 120 degrees separation between the 3 equatorial bonds. So trigonal bipyramidal, class of AB5, this example for phosphorus pentachloride, or PCl5, that's in this class of the general form of AB5. Next, we're into this class, so AB6. So we have a central atom, then with 6 bonds around the central atom. With 6 bonds around the central atom, we call this octahedral molecular geometry. Here's A in the middle, then B, 1, 2, 3, 4, 5, 6. With 6 groups around the central atom, the bonds here are all 90 degrees, separating all 6 of those atoms from the central atom. So we have 2 going up. Then in this plane, we have 1, 2, 3, 4. So those 4 in the plane are all separated by 90 degrees, then 1 going up, then 1 in the plane. That then is also separated by a right angle of 90 degrees. So 6 groups, 6 bonds, we call this octahedral molecular geometry. Let's look at an example of this class of AB6. So AB6 is the class. An example of this is sulfur hexafluoride. So SF6, sulfur is in the middle, then 6 fluorine atoms around that central sulfur. So 2 going up and down, then 4 in this plane. All of these are separated for the class of AB6. For octahedral geometry, these are all separated by 90 degrees. This is a nice way to picture it too, to see that separation of 90 degrees. That's not to say though that this bond and this bond here, these are separated still by 180 degrees. This one and this one, this is also separated by 180 degrees. So the 90 degrees just separates the bonds from the central atom. So this bond to this bond, or this bond to this bond. So the ones directly close to one another, those are all separated by 90 degrees. This is a nice summary table, so table 10.1 showing 2, 3, 4, 5, 6 electron pairs around the central atom. So linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. When we have all bonds from a central atom and no lone pairs yet, then this arrangement of electron pairs is the same arrangement as its molecular geometry. If we're starting to add in lone pairs, then we'll see differences here, but we'll get there soon in chapter 10. So here are some examples as well in this table. So it's handy. It also shows the bond angles here. So 180, 120, 109.5, 120, and 90, and then just 90 for octahedral. So given this background on Vesper, let's go into this practice problem and let's answer how many electron groups or how many regions of electron density a group counts as any bonds or any lone pairs. So how many groups, how many bonds plus lone pairs around the central atom of sulfur? And then what phrase best describes the arrangement of these electron groups around the central atom of sulfur? To solve for these structures, it definitely helps if we draw out the Lewis dot structure first. We may think that, oh, SO3, that just means 3 groups around sulfur. That is not necessarily true. Again, we're looking for how many bonds and how many lone pairs are off that central atom of sulfur. We can't tell just by looking at the formula how many lone pairs might there be on the central atom. So the very first step is always going to be to draw the Lewis dot structure for that formula that we're given. To draw this Lewis dot structure for SO3, we need to decide which atom will be in the middle and how many total valence electrons are we working with. On the periodic table, oxygen is further up than sulfur and electronegativity increases going up a group. That means the smaller electronegativity goes to sulfur, so we're going to put sulfur in the middle. We're also told in the hint of the problem that the central sulfur atom is here, so we could also go based off that, but we also know by looking at the electronegativity comparisons that sulfur is less electronegative. The least electronegative atom will go in the middle. Then both sulfur and oxygen are in group 6A, so this has 6 valence electrons. There are 1, 2, 3, 4. So 6 valence electrons for both sulfur and oxygen, so this times 4, that's 24 valence electrons to work with. In drawing the skeleton around this, we'll do 3 oxygens, then we'll draw in the bond. Within each of these bonds is 2 electrons, so this is 6 electrons we've used up so far. With the 18 electrons remaining, we'd start to put lone pairs around the more electronegative atoms or the outer atoms. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 electrons we've used up. Are we done? Well, we need to check, is the octet rule fulfilled? Well, for each of the oxygens, 1, 2, 3, 4, 5, 6, 7, 8. So yes, for oxygen, the octet rule is satisfied. However, we need to check for sulfur too. For sulfur, we have 1, 2, 3, 4, 5, 6. For sulfur, no, the octet rule is not yet satisfied. What do we do if that happens? We need to take lone pairs into a double bond. Can we take this lone pair, put it into a double bond, and will then that lead to a satisfied octet for sulfur? Well, let's see, it'll be 1, 2, 3, 4, 5, 6, 7, 8. So then yes, sulfur would be okay with a double bond here, single bond, single bond. The full result of just doing that with a lone pair of electrons, there are 2 lone pairs of electrons remaining on this oxygen, now with a double bond. Do we still maintain this oxygen's octet by doing that? Well, 1, 2, 3, 4, 5, 6, 7, 8. So yes. This structure works. We have obeyed the octet rule. We've used up all the valence electrons here, so this is a good structure. Hopefully you're wondering, well, couldn't we have pulled in a lone pair from this oxygen instead? Or what about this oxygen? Yes, that would definitely work for either of these 3 oxygens. If we can do that with either of these 3 oxygens, that means we are looking at a structure with resonance. This structure has resonance, and let's see what those different 3 structures would look like. So double bond, single bond, single bond, double bond, single bond, single bond, double bond, single bond, single bond. Also take note that for the oxygens with single bonds, they have 3 lone pairs around them. So single bond, 3 lone pairs, single bond to oxygen, then 3 lone pairs. Whereas the oxygen that's double bonded to sulfur, that's a double bond and 2 lone pairs. So double bond, 2 lone pairs. These are 3 resonance structures of sulfur trioxide, or SO3. So molecular compound, sulfur trioxide, these 3 structures represent sulfur trioxide. It's not this one alone, not this one alone. All 3 of these resonance structures represent this molecule of sulfur dioxide, or this compound, I could say, of sulfur dioxide. If we have resonance like we do here, we can actually use any of these 3 resonance structures for the next steps in figuring out its geometry. Why can we use any one of them? Well, we'll notice we have 1, 2, 3 groups around this sulfur, 1, 2, 3, 1, 2, 3. So it doesn't matter which one we pick because they all have 3 groups around the central atom of sulfur. And so what you may be thinking or wondering about is these regions of electron density, or these electron groups around the central atom. A double bond just counts as 1 group or 1 region of electron density. Single bond, another group. Single bond, another group. A double bond altogether still just counts as 1 group because it's just 1 atom that's bonded to the central atom of sulfur. This double bond is all in the same space, so it just counts again as 1 region of electron density off the central atom. We'll see this concept come back again. Just wanted to give you a preview of this. So double bond, also just 1 group around the central atom, just like these single bonds as well. So step 1 was to draw the Lewis dot structure. Here we did. Now we can move forward with any of these 3 resonance structures. Next, we need to count the electron groups around the central atom. Each one of these just counts as 1 electron group. If we see a lone pair of electrons, that is 1 group. If we see a single bond, that is 1 group. Double and triple bonds, those are also just 1 group. Looking at any of these 3 structures, we can see 1 group, 2 groups, 3 groups. Double bond counts as also just 1 group. 1 group, 2 group, 3, 1, 2, 3. We can see now from step 2, there are 3 electron groups around the central atom of sulfur in SO3, or sulfur trioxide. So again, we're not just going to look at the formula itself, we need to draw out the Lewis dot structures. That's number 1. We have to draw out the Lewis dot structures to know how many groups are around the central atom. How many regions of electron density, how many electron groups are around the central atom. From drawing out the Lewis dot structure, not just by looking at the formula, we figured out there are 1, 2, 3 groups around sulfur. Now in step 3, we pick the correct electron group arrangement given that there are 3 groups around the central atom. The 3 groups here happen to all be 3 bonds, 2 single bonds, and 1 double bond. Again, we will eventually see where there are not just bonds, but there are lone pairs of electrons around the central atom as well. Here, just 3 bonds, 3 groups around the central atom. We know from Vesper that the 3 negatively charged regions of electron density, either in bonds or lone pairs, will repel one another. Negative charges don't want to be near one another. Those groups will spread out as much as possible around the central atom. So here the most likely arrangement of electron groups around a central atom is one that keeps those groups as far apart as possible. These are the groups we looked at in the last few slides. If there are 2 electron groups around the central atom, we know that's linear. 3 groups, that's that idea of a trigonal planar geometry. Because there are 3 electron groups around the central atom of sulfur in this compound, and we figure that out importantly by drawing the Lewis dot structure. Do not rely on just looking at the formula. Draw the Lewis dot structure to figure out the number of electron groups. So with 3 groups around the central sulfur, we know this is a trigonal planar geometry. So here's what we were looking at previously. So AB3 class, 3 atoms bonded to the central atom, 3 groups around the central atom. That is trigonal planar. So similar to boron trifluoride, here these were all single bonds. For our practice problem, we had 2 single bonds and a double bond. That is still, though, just 3 groups in total around the central atom. So this is trigonal planar. Here's our completed table. We have 3 groups around the central atom. This is trigonal planar for SO3. Just another reminder here, to figure out this style of problem, always draw the Lewis dot structure first. Now let's go into this topic of naming the shape of molecules with 1 central atom and no octet rule exceptions. For predicting our molecular geometry, we know first and foremost we must draw the Lewis dot structure. From the Lewis dot structure only can we then count the number of lone pairs on the central atom and the number of atoms bonded to the central atom. So we're drawing the Lewis dot structure, then we count the number of either lone pairs or bonds. We're counting both that are coming from that central atom. Where 1 lone pair counts as 1 group, 1 single bond counts as 1 group, and 1 double or triple bond, those both also count as just 1 group. After we know the number of total groups, then we use Vesper to predict the geometry of that molecule. Let's try this practice problem for carbon dioxide. What's the very first thing we should do? Well, let's draw the Lewis dot structure. Before we draw the Lewis dot structure, here's just another blurb that we've heard now on Vesper. So as mentioned, Vesper helps us decide the shapes of molecules with a central atom. Negatively charged electron lone pairs or bonds, they all want to spread out as much as possible because negative charges repel one another. To avoid having negative charges close to one another, we'll spread out those groups as much as possible, as seen by the different bond angles, or the different angles between lone pairs and bonds as well. So the best shape is going to be the one that keeps electron groups as far apart as possible. To draw the Lewis dot structure for carbon dioxide, we need to first figure out what's the least electronegative atom and put that one in the middle. Electronegativity increases going left to right. It also increases going up a group. Carbon then is less electronegative than oxygen, so we'll put carbon in the middle. Then 2 oxygens on the side. The total number of valence electrons we can use here for carbon is 4. For oxygen, that's 6. There are 2 of them, so 6 times 2 is 12 plus 4. We have 16 electrons we can work with in this bond so far, so 1, 2, 3, 4. We've used up 4 electrons just to draw the skeleton. Now we need to add in these 12 to the more electronegative atom. The more electronegative atom or atoms are going to be the ones on the outer. So the ones on the outer regions of the molecule. The non-central atom is the more electronegative. So with 12 here, we might do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We've used up all valence electrons, but it's pretty clear that probably this middle carbon doesn't have a complete octet. So 1, 2, 3, 4, we need 4 more electrons around that carbon. To make that happen, we know we can try bringing in lone pairs. So lone pair, we could put it here. That's still just 3 bonds from carbon. Carbon likes to have 4 bonds. So carbon with 4 valence electrons needs 4 bonds around it. Or it prefers to have 4 bonds around it. So that would look like a bond here. That probably means we should go ahead and take another lone pair and put it in here. We don't want to take another lone pair from this oxygen because that would start to mess with the formal charges, and we know we don't want to mess with the formal charges too much. So if we bring in this lone pair from one oxygen, another lone pair, but from the other oxygen, that will help keep the formal charges minimal or closer to 0. The result of pulling those electrons in then is 2 double bonds to both oxygens. Then the lone pairs that are left, 1, 2, 3, 4. So 4 electrons here, 2 lone pairs here as well. Does the central carbon have a happy octet? Well, hopefully, right? 1, 2, 3, 4, 5, 6, 7, 8. To show for one of these oxygens too, we have 1, 2, 3, 4, 5, 6, 7, 8. So we've satisfied the octet rule. We've used all valence electrons. This is a good structure for carbon dioxide. The formal charges here on carbon, this is 0, and the formal charge here on both oxygens are also 0. As a quick review on formal charge, let's do it for oxygen. Oxygen has 6 valence electrons by looking at its placement in the periodic table. Then the number of electrons here around it, 1, 2, 3, 4. So 1, 2, 3, 4, minus 1/2 times the total number of electrons in bonds. That is 1, 2, 3, 4. 6 minus 4 is 2, then minus 2 is a formal charge of 0 for this oxygen, and for this one as well, because they have the same type of bonding. So double bond here, then 2 lone pairs. Let's go ahead and show carbon too. Carbon has 4 valence electrons by looking just at its placement in the periodic table. It has no electrons around it as lone pairs. As a reminder for formal charge, each of these electrons counts here for this number. Then the number of electrons in bonds around carbon is 1, 2, 3, 4, 5, 6, 7, 8. So 1/2 times 8. 4 minus 4 is 0. The formal charges here are good. So we check the octet rule. We use all the valence electrons, and we have all 0 formal charges. That is good. That's the ideal formal charge. -1 and +1 are just okay. If we need to have a minus formal charge, that should be on the more electronegative atom, just for a quick review on formal charge. Formal charges of +2 and -2, those are really not ideal. Now that we have this Lewis dot structure for carbon dioxide, we can count the groups around the central atom of carbon. What counts as a group again? Well, it's any lone pairs, any single bonds, and either double or triple bonds. Just to emphasize again that double or triple bonds only count as one group of electrons, not two or three. That means for our structure of carbon dioxide, the correct Lewis dot structure for carbon dioxide, this is a group and this is a group. So two regions of electron density, or two groups of electrons, groups of valence electrons to be specific, around the central atom of carbon. So two groups around the central atom, we know what geometry that leads into. To keep two groups as separate as possible, we will have linear molecular geometry where that bond angle between the two atoms is 180 degrees. So we'd separate these by 180 degrees here, and then on this side as well. So two electron groups around carbon dioxide. Just to point out again here importantly that both of these groups are bonds. So one group is a double bond, the second group is also a double bond. We would normally go on to step 4, which is a really important step, where we also assign each lone pair group to a place in the electron group structure. We'll get into some practice with looking at lone pairs around that central atom that I keep mentioning. The reason these are important to keep separate from bonds, yes, they still count as groups, so lone pair bonds, either single, double, or triple bonds, are each just one group. But importantly, lone pairs of electrons take up a little more space than a bonding pair of electron groups. So when we start to look at lone pairs around that central atom, we should try to keep lone pair electron groups as far away as possible. So for example, a lone pair of electrons off the central atom, that takes up a lot more space, or at least a little more space, depending on the structure, compared to a bond from that atom. So this lone pair of electrons takes up more space than a bonding pair of electrons like this. So once we come back to this, we'll keep this in mind. For carbon dioxide, we just have two double bonds and no lone pairs. So lone pairs would take up more space, then we'd go in and place each bonding electron group around the central atom. So we've been thinking about the number of groups or the number of regions of electron density around the central atom. Just in case you hear this terminology as well, the word ligand can be used to mean an atom or group of atoms bonded to something. So that means here we have two groups around the central carbon. We have two regions of electron density. In case you see this terminology then, this also means we have two ligands around the central atom. But here we'll stick with talking about groups and regions of electron density, and then bonds or lone pairs of electrons, where the lone pairs of electrons are our non-bonding electrons. So lone pairs would be considered non-bonding. They're not bonding X to some other atom. They're just a lone pair of electrons off that central atom. We know carbon dioxide, we've identified that two groups are bonded to that central atom. And now to start to differentiate if we have bonding groups or non-bonding lone pair groups. To name the shape of the molecule, we only consider the bonding electron groups. And so we'll get more into this point. Most electron group structures can lead to several possible shapes depending on how many lone pairs there are around the central atom. We'll look more into this in the next part of chapter 10. To start familiarizing you with this, we can have electron groups. For instance, 2 electron groups, those are 2 atoms bonded to the central atom, or 2 ligands. For 3 electron groups bonded to the central atom, when we have the central atom with 3 bonds to that central atom, we know this is trigonal planar. However, when we have a central atom, we have 2 bonds to it and then a lone pair, that is still 3 electron groups in total. Now, however, we call this bent geometry. We'll look a lot more into this again in the next part of chapter 10. We're starting to incorporate lone pairs around the central atom as well as bonds. So 3 groups in total, 3 bonds, 3 groups in total, 2 bonds, and then a lone pair. For 4 electron groups, we saw a tetrahedral, so that central atom, and then 4 bonds from that central atom. Trigonal pyramidal is what we call still 4 electron groups around the central atom, but here we have 1, 2, 3 bonds, and then that 4th electron group is a lone pair. Then still in the category of electron groups, we have 1, 2, 3, 4 around the central oxygen here. 2 of these are bonds, and then 2 of these are lone pairs. This is what we call now bent geometry. We'll go more into this, and there's a nice table I'll show you in the next part of chapter 10, or the last part of chapter 10. The next part will be the last part of chapter 10. We know carbon dioxide, 2 groups around the central carbon. 2 groups around the central carbon. This is a linear geometry. We have no lone pairs, only bonding groups around the central carbon. For this category of 2 electron groups, we can only have bonds around the central atom. So you'll notice for linear, it's just 2 bonds. Then when we get into 3 electron groups, for example, that's where we could see 2 bonds and then a lone pair. So next part of chapter 10, we'll go more into this, and I'll show you a nice summary table. Example 10.1 is a good one to look at in the main slide deck. I'm going to go through just a few of these with you. So 10.1, let's do B and D together. So in using the Vesper model to predict the geometry of both of these, the strategy here is to, of course, draw the Lewis dot structure first, then find the arrangement of electron pairs, then find the arrangement of bonding pairs. So electron pairs, then bonding pairs. Electron pairs are the lone pairs. They take up more space than bonding pairs of electrons. From there, we determine the geometry just based on the bonding pairs. So let's start to look at this, and then again, we'll do more in the next part of chapter 10. Fluorine is definitely more electronegative than oxygen. Oxygen has 6 valence electrons. Our fluorine is a halogen, has 7 valence electrons times 2. In total, we have 20 electrons to work with, and we need to put the least electronegative atom in the middle. Then we just draw a skeleton with single bonds between the central atom and then the 2 fluorines. So now I've used up 1, 2, 3, 4. Each bond contains 2 electrons, so now we have 16 remaining. These 16 remaining electrons should go around the more electronegative atoms, in this case, definitely fluorine. Oxygen is very electronegative as well, but fluorine is the most electronegative. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I'm placing these around the fluorine so that the fluorine has a complete octet. We don't go over that amount, so I can only put in 6 and 6. Then with 4 remaining, we have to put those on the only remaining oxygen atom in the middle. We only need to think about pulling in a lone pair to form a double bond if we don't have happy octets. Do we have happy octets here? Well, 1, 2, 3, 4, 5, 6, 7, 8. Yes for oxygen. Then 1, 2, 3, 4, 5, 6, 7, 8. Yes for both of the fluorines. So if there are happy octets, we don't need to form any double bonds. That means this structure is sound, this one is ready to go. We can start to notice we have 2 bonds from the central oxygen and then 2 lone pairs also around the central oxygen. So for the total number of groups, we have 2 groups that are single bonds. We also have 2 groups that are lone pairs. A lone pair counts as 1 group. So 1 lone pair, a second lone pair, that's 2 groups here for a total of 4 groups around the central atom. So the electron pair arrangement is considered tetrahedral because we have 4 groups around the central atom. What about the shape? For the shape, we have 2 bonds and 2 lone pairs of electrons. So here we have 4 electron groups. We have 2 bonds and 2 lone pairs. This shape then is actually considered bent. So for the electron pair arrangement, we look at all total number of groups. For the shape, though, we differentiate how many bonds versus lone pairs, so this is considered bent. And a table with this sort of information we'll go into a lot more in the next part of chapter 10. Just to come back to this table to show you a preview of what I mean, we have the arrangement of electron pairs. For the arrangement of electron pairs, we'll look at the total number of groups. For the molecular geometry or for the shape is when we start to differentiate lone pairs from bonding pairs. So total number of groups, the arrangement of electron pairs, that is considered tetrahedral for our current practice problem. For the molecular geometry, however, that's when we start to compare number of lone pairs versus bonding pairs. So tetrahedral arrangement of electron pairs, but for the molecular geometry, we are looking at bent molecular geometry. So arrangement of electron pairs is tetrahedral. Then for the molecular geometry or for the shape, however, that is now considered bent. So bent is a classification of tetrahedral. Again, we'll look at an expanded table that will be really helpful in differentiating electron pair arrangement versus molecular geometry. Let's do this next example now, so for D. In figuring out the Lewis dot structure, we would first look at what is the least or more electronegative. These are all the same, so we can just write at the skeleton here. For the number of valence electrons, we need to account for that minus charge, meaning there's an extra valence electron. Iodine is one of our halogens. It has 7 valence electrons times 3, that's 21, plus it's an anion. For an anion, we add on an additional electron here, so now we have 22 to work with. We would put these electrons around the more electronegative atoms or the outer atoms. The non-central versus outer atoms, they're all the same. So because they're all iodine, it doesn't really matter where we put these lone pairs. That's 1, 2, 3, 4, 5, 6. Then 1, 2, 3, 4, 5, 6. Then to not disobey the central iodine's octet rule, it already has 1, 2, 3, 4. That means we can only do 5, 6, 7, 8. I didn't yet account for the 4 electrons here in the 2 bonds, so now we have 2 left. So let's just double check that. We've used up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So we had 22. We have 2 more to use up. Can iodine have an expanded octet? That would mean that the principal quantum number has to be greater than 2. Iodine has 53 electrons, so we'll definitely see an N value greater than 2. That means that I can have an expanded octet. We are focused on the non-exceptions, but I wanted to show you how this would work in adding on another lone pair here off of the central atom. This atom is in the middle, so it can sort of share its electron density between both of the outer iodine atoms. That's why it's better to make an expanded octet on the central atom. Again, we're focused on the non-exceptions. I just wanted to show you how this one would work. For this structure, and because it's an anion, we remember to put brackets around it and then show the charge right here. We're going to see what's happening when we have 1, 2, 3 lone pairs of electrons around the central atom and 2 bonds around the central atom. So we've been focusing on identifying the arrangement of electrons. To do this, we look at all types of groups. Then, as we just saw in identifying the molecular geometry or the shape, then, as we just saw, and as we'll go into more in the next part of chapter 10, if we're looking at the molecular geometry or shape, we would then need to differentiate bonds from lone pairs. For just the arrangement of electrons, we know we counted 1, 2, 3, 4, 5. For 5 groups around the central atom, and just looking at the arrangement of electron pairs, this is considered trigonal bipyramidal. For the molecular geometry, however, this would only be trigonal bipyramidal for its molecular geometry as well if we had all 5 bonds. For our current example, we have 2 bonds and 3 lone pairs. So trigonal bipyramidal for 5 total groups around the central atom. If we want to spread apart the lone pairs as much as possible, because those lone pairs take up more space than a bond, then we should put the I atoms in the axial positions and then the lone pairs in the equatorial position. So we can spread out the lone pairs as much as possible. So there's 120 degrees between each set of lone pairs. So within the category of trigonal bipyramidal for the arrangement of electron groups, with 5 total groups where 2 of those groups are bonds and 3 of those groups are lone pairs. So 2 of them are bonds, 3 of them are lone pairs. This starts to look like our linear molecular geometry. So within this category of trigonal bipyramidal, when there are 2 bonds to the central atom and 3 lone pairs, we actually consider this linear molecular geometry, all within the category of trigonal bipyramidal arrangement of electrons. So we'll look at this a lot more in the next part of chapter 10. And so I talked about this on the last slide, where lone pairs, they take up more space. They occupy more space than a bond. So lone pairs will preferentially occupy those equatorial positions. They can be even more spread out. That leaves the two bonds here in the axial position, again leading to linear molecular geometry, still under this category of trigonal bipyramidal. And for bonds here in the axial position, we know that bond angle between the two atoms in bonds is 180 degrees. So we'll do more geometry in the next part of chapter 10. That will be the last part of chapter 10. Hope you're all doing well. Let me know if you have any questions, and then I will talk to you soon.